In the previous video, we derived the product of exponentials formula to calculate t of theta, the configuration of the end-effector frame B relative to the fixed space frame S when we're given the joint positions theta. In that formula, the joint screw axes are defined in the S frame fixed to the world. In this video, we derive an alternative version of the formula where the joint screw axes are defined in the B frame fixed to the end effector. We use the same RPR robot as an example. First, let's move the robot to its zero configuration. As before, we define M to be the configuration of the B frame when the robot is at its zero configuration. Now we rotate joint 1 by an angle theta 1. The motion of the B frame is a rotation about the screw axis of joint 1. We will represent the screw axis in the B frame as B1 with the angular component omega 1 and the linear component V1. Since the screw axis has rotation, omega 1 is a unit vector. Since the screw axis is aligned with the z-axis of the B frame, omega 1 is equal to 0, 0, 1. The linear motion V1 can be obtained by visualizing a turntable at joint 1 rotating and measuring the linear velocity at a point at the origin of the B frame. Since the distance between the joint 1 and the B frame is 3, the linear velocity V1 is 0, 3, 0 in the B frame. We could also calculate this by defining a point Q1 on the axis of joint 1, where Q1 is expressed in the B frame. Then V1 is minus omega 1 cross Q1. Now that we have the screw axis B1, we can calculate the B frame configuration t of theta. We simply apply the body frame transformation corresponding to motion along the B1 screw axis by an angle theta 1. This transformation is e to the bracket B1 times theta 1. Since it is a body frame transformation, it post-multiplies m. Now suppose we change joint 2, extending it by theta 2 units of distance. The screw axis B2 corresponding to joint 2 has zero angular component omega 2, so the linear component V2 must be a unit vector. If we imagine the whole space translating at unit velocity along joint 2, a point at the origin of the B frame would move with a linear velocity V2 equal to 1, 0, 0 expressed in the B frame. Therefore, the screw axis B2 is defined as 0, 0, 0, 1, 0, 0. The new configuration of the B frame, t of theta, is obtained by right multiplying the previous configuration by e to the bracket B2 times theta 2. Notice that the previous motion of joint 1 does not affect the relationship of joint 2's screw axis to the B frame because joint 1 is not between joint 2 and the B frame. Therefore, B2 is the same as the screw axis of joint 2 when the robot is at its zero configuration. Finally, let's rotate joint 3 by theta 3. The screw axis B3 is a pure rotation about an axis out of the screen, so the omega 3 vector is 0, 0, 1. Rotation about this axis induces a linear motion V3 equal to 0, 1, 0 in the B frame. The new configuration of the B frame, t of theta, is given by right multiplying the previous configuration by the new body frame transformation. Again, the previous motions of joints 1 and 2 do not affect the relationship of joint 3's screw axis to the B frame because they're not between joint 3 and the B frame. Therefore, B3 is the same as the screw axis of joint 3 when the robot is at its zero configuration. In summary, we've derived a procedure for forward kinematics when the screw axes are expressed in the B frame. First, define the M matrix representing the B frame when the joint variables are 0. Second, define the B frame screw axes B1 to Bn for each of the n joint axes when the joint variables are 0. Finally, for the given joint values, evaluate the product of exponentials formula in the B frame. Comparing the two product of exponentials formulas in the S frame and the B frame, the major differences are the frame of representation of the screws and whether M is on the right side or the left side of the sequence of matrix multiplications.